For this Lab 5, we were asked to create our own lab investigating one of the principles investigated during this course. I decided to observe conservation of momentum, specifically in reference to elastic collisions. I used the conservation of momentum and energy principles to create a computational model through GlowScript to model the observed motion of two cards colliding elastically. Through this computational model, momentum of the two cards as well as their kinetic energies were able to be observed and analyzed. The momentum principle, as well as Newton's second law, was essential in the creation and understanding of the computational model. The main principle used in plotting the motion was the momentum principle, knowing that momentum is equal to mass times velocity and that the total momentum will remain constant through the collision, giving no external forces are acting on the objects. In this situation, the entirety of the momentum of the system is in the first card during the beginning, as the second card begins with zero momentum and zero velocity. However, at the end, the whole of the momentum is contained in the second card, as the first card has a final velocity of 0 after interacting with the second card. Additionally, the kinetic energy of the system should be conserved by definition of an elastic collision, meaning the initial kinetic energy will be the same as the final kinetic energy. The equations used in this observation are momentum is equal to mass times velocity and kinetic energy is equal to 1/2 times mass times velocity squared. In the computational model, it is also necessary to understand the relationship between momentum and force using the equation that momentum is equal to force times change in time. To find the values of the initial velocity and positions of the masses needed for the creation of the computational model, I used Tracker to measure the motion of an elastic collision between two cards on a frictionless ramp. The data collected regarding the x position of the cards was compiled into a graph of position versus time through Tracker and was moved into a Google Sheets document for later use. This allowed for me to find the initial position of the first cart, which is at the origin, and the initial velocity, which is 0.835 meters per second in the positive x direction. For the second cart, I was able to find the initial position to be 0.735 meters to the right of the origin with an initial velocity of 0 meters per second. Additionally, the mass of both carts was 0.59 kilograms. The first model I used in this lab was through the app Tracker, where I was able to observe the motion of two carts colliding elastically as shown in this video here.
The collision.
In order to configure this model to correctly observe the motion of the carts, I calibrated the frame speed to be 33 frames per second, the length of the carts to be 0.3 meters, and the axis to be in the same direction of the motion of the carts. I tracked the motion of the center of mass of each cart, and Tracker produced a position versus time graph of each of them. From these graphs, I found the initial and final velocity of cart 1 to be 0.835 meters per second and 0 meters per second respectively, and those of cart 2 to be 0 meters per second and 0.832 meters per second respectively, by dividing the change in position by the change in time of each cart. In order to avoid any major interferences that may have come from acceleration due to friction or human interaction with these carts, I measured these velocities during a time interval in which they were close to the collision. Using these values, I was able to create a GlowScript computational model of this collision shown here. I began by creating both masses represented in this situation by spheres. I set the mass of each to be 0.59 kilograms, the initial velocity and position of both carts to be the same as what was observed in the video, and the momentum of the spheres to be mass times velocity in the x direction, since this was the only way in which the carts moved. Additionally, I set the time interval to be equal to that of Tracker, being 0.033 seconds per frame. To model the motion and collision, I created a while loop running until 3.033 seconds, which was the time interval of the observed video. In this loop, I defined the force on each ball, which was 0 during the time in which they weren't in contact. However, given their radiuses were overlapping, the force of one ball on another was equal to a spring force said to be equal to, in which the constant was said to be equal to 10 this program, times the vector difference between the two center of masses, representing the force they had on one another. Additionally, using Newton's third law, we know that these forces are equal and opposite, meaning both spheres exert the same force on one another. Following this, the momentum and position of the balls were updated using the relationship that momentum is equal to force times the change in time. Finally, the momentum of the balls, their position, and their kinetic energy were plotted on different graphs. Here is the computational model of this collision in action, as well as the production of the momentum, position, and kinetic energy graphs. Viewing the momentum graph created through GlowScript, the momentum of the first ball is shown in red, the one of the second is shown in green, and the total momentum is shown in blue. As discussed in the beginning, the first ball begins with all the momentum in the system, and at the end, the second mass is the entirety of the momentum in the system. Additionally, we can see that the momentum remains the same throughout the collision. In a similar fashion, the kinetic energy is the same before and after the collision, with the first mass having all the kinetic energy in the beginning and the second mass having all the energy at the end. The last graph we see is the position graph. Comparing the computational to that of the observed position, they are very similar, the second mass shown in green initially having no velocity, and the first mass shown in red having no final velocity. The one difference is that the computational balls show the center of masses of the spheres getting closer. The reason for this is that the coding in the model, I use a spring constant allowing the balls to come closer to one another in reference to their center of masses. Additionally, the radiuses of the spheres are smaller relative to that of the cards. This computational model does a good job in showing the principle of conservation of momentum in elastic collisions, since the momentum graph shows a constant total momentum throughout the entire interaction. Additionally, this model shows the behavior of kinetic energy in the system in that it will be the same initially as it is at the end. Modeling this energy from the observed video was difficult, given the instantaneous velocity changed rapidly since the change in position between frames was small and slight human error made it difficult to measure constant velocity from these models. However, this conservation of energy is seen in the observed model, given that the velocity of the first cart initially is very similar to that of the final velocity of the second cart, and since they both have the same mass, their kinetic energies will be very similar. The velocity of the second cart is slightly lower, but this may come from human error in tracking the center of mass, as well as slight friction that may come from the frictionless track. In the model, it is important to note that there's a drop in kinetic energy during the moment of collision. However, this stems from the fact that collision in this model is simulated using a spring constant, meaning there is an overlap in the radii of the spheres during their interaction. However, the conservation of kinetic energy is evident in the fact that the initial kinetic energy is equal to the final kinetic energy.